Welcome to Study Loop.
Okay, so we're doing chapter 29, problem 31. So in this problem, we have a circuit with a resistor here, and these two ends of the circuit, these two wires are connected by a metal bar. Let's draw that a little bit better. So they're connected by a metal bar here. And this is all in a B field that is pointing out of the page, sorry. So B field out of the page. This is a length L, and they tell us it is moving towards, this bar is moving towards the left. Okay, so let's write some of these things down. This is 0.36 meters is the length of the bar. Tells us the resistance of the resistor is 45 ohms, and it tells us the magnitude of the B field is 0.65 Tesla. Okay, so we want to figure out the direction of the induced current in the circuit. So to do that, we use Lenz's law. And Lenz's law is the one that says the induced current produces a B field that opposes the change in magnetic flux. Okay, so let's look at this flux here for a second. We know the magnetic flux is the B field times the area. So the B field is constant, right? So this is constant. But as the velocity moves to the left, this loop of our circuit is decreasing. So that means our flux is decreasing. So if our flux is out of the page and decreasing, to oppose that, the induced magnetic field must be out of the page. Okay? So now we got to use the right-hand rule and figure out which direction of a current in this loop produces a B field out of the page. And if you do the right-hand rule, you'll see that this is going to be counterclockwise. Okay? Cool. So now let's figure out what the current value is, because we're going to need that for the second part of the problem. So let's figure out the magnitude of this induced current. And this is given by the EMF over the resistance, which we know the EMF is given by Faraday's law as the negative change in magnetic flux. So we're just worrying about magnitudes here, so we can drop the negative sign, and we can simplify this to B dA dt, since B is the constant one. And now we can even simplify dA dt, so this becomes B L over R V of t. Okay, so it says we want to do this at the instant where it's moving 5.9 meters per second to the left. So we can now plug everything in. So we have 0.65 Tesla times 0.36 meters times 5.9 meters per second, all over 45 ohms. And this comes out to being 0.0307 amps. Cool. So now we can figure out the second part of the problem, which is asking about the rate of work. So the rate of work is also known as a power. So we can find this two different ways. One we can do by the mechanical work of the force times the velocity of this bar is moving. But by energy conservation, we know that this is exactly equal to the thermal power loss, which is given as I squared R in the circuit. So since we know I from the first part, we can easily calculate this. So the power is given as 0.0307 squared times 45 ohms. And this comes out to being 0.042 watts. Awesome. And again, since we have a counterclockwise current, this is the magnitude of the current, and this is the power dissipated. That's it.